All right, everybody, how we doing today? Good. Doing good? How's the classes going? Pain? Not enough pain? More homework? Less homework? All right, so I got a few questions to ask everybody. So, did everyone see the announcements that I made over the weekend about posting content notes? Is that helpful? Was the video working? Yeah? You can see the PDFs? Let's click on this just to make sure everyone have this on record. See that right there? Just click on that. Takes you to an external link. All good. Now let me see if you click on this. You can see that I do other classes here, right? There's good references. Hopefully everyone is seeing what we're doing here. Yeah, I do another course here today. Signals and systems for my EEs, if you guys want to know. Just take signals and put them into systems. Sounds like circuits, right?
Isn't that like the hardest class?
Has anyone here heard about discrete mathematics? Where you have to just memorize all these definitions, and it's not like numbers, it's all just words. And yeah, that's kind of signals and systems. Just theories and what's a signal, what's a function, define a function.
So you're not really dealing with numbers?
Kind of, but you're more generalizing signals. It's a pretty good class for 360 is a third year class. Right after you take your advanced standing, that's one of the next classes we have. I think 221 is when everyone starts splitting into their advanced standing classes. That's probably what I think by the third year everyone should be split up into your EE cores and your CPE cores. Is that correct? Unless they changed it this year, I'm not so sure. They're always changing something. I think EEs are doing 3 labs now, right? Right? Does anyone know?
It's 4 now.
4? Yeah, I'm hearing there's a petition to make it 3 now, which is interesting. So, because you guys can touch resistors, power supplies, whatever you want, and I'm like, it used to be 5. I took 5, which I liked it, but I guess this is why I asked the questions to our second years. So,
Would you say 360 was the hardest
360?
class that you took as undergrad?
Electromagnetics was the toughest class. I like that one. That one was, you just start learning about what a resistor truly is. And let me show you. These little components right here, your resistors, you start realizing what they truly are, and there's a lot of magic that happens in it. You want to know a hint? Electric forces. Electric fields. Because you have a voltage, and then there's an electric field, there's a distance, voltage drop. That make sense?
Not yet.
Don't worry, we'll get to that class in next year or 2. Anyways, let's see what else we have here. So everyone's aware that there's videos. Did anyone see the discussion that I posted? Did anyone use it? No?
What is it?
So I was hoping anyone would have replied. Let's check my announcement. Hi, content. I've added a module with the discussion page. Leave any questions so that we can go over them in class. But as I see, I want to ask some questions today, and that's why I have this handy-dandy camera to go over them, whoever wants to be my guest to write them. So does that make sense? Let's see. Let's see if this bothers anyone. Test reply. David. Hopefully everyone gets this should send a notification. So I think if you start using this discussion board, I think it notifies people. I'm not so sure how it works. I really don't. So let me know. I'm trying to get as much feedback as I can so that we can go over. Yes?
I found a question that I was asking you earlier.
Yeah, sure.
Should I bring it up? Or not yet?
Yeah, let's bring it up. All right. Let's do our funny thing.
This is what I was asking. It just says determine Vy. It's question 38. Determine Vy in the circuit of figure P138.
Let's go over this. You want me to do this? Is this your homework?
Yeah, I mean, I finished it, but I don't know if I did it right. So
All right. So instead of using our handy-dandy camera, I'm going to do the following. P138, right?
yeah.
And we got 12 volts. And we are given current. Let's label that a different color. I'm track my colors now. And this one is a 5 ohm resistor, plus minus Vx, 5 ohms. I got 10 ohms right here. I in this is going to equal to 0.1 Vx, 2 plus minus Vy. Is this a homework problem that you already finished?
Yeah.
Or is this for next homework?
I just don't. I got to an answer, but I'm not sure. Like, I'm not confident.
All right, let's try it. So let's see here. It gives you a circuit, and it already gave you this. I given. Does that make sense right there? Let's go over some fundamentals. Let's use our nice blue marker. What's the voltage right here?
0.
What's the voltage over here?
12.
So far, so good, right? What's this resistor? 5.
5 ohms.
So what's this Vx going to equal to?
V equals R, so that'll be
I, and then R, right?
yeah.
What's our R?
5.
What's our I?
1.2.
Does that make sense? And then it's 1.2 times 5, so 1.2, 2.4. Let's try here so that people can see what I'm doing. 1.2 times 5.
Okay.
6? Is that clear?
Yeah.
So we solved for the voltage drop of the resistor, right? So let's bring out our little happy person. Remember, you guys like this little guy? Just a little guy just running around the circuit. Let's go up the stairs, right? We're going up the hill, right? So if I'm at 0, I'm going up the hill, right? 12 volts, right? I'm over here, right? We're still on the same page, right? We're going to go down the hill. We're going to go down the hill, right? That means we're going to subtract, right? Subtract Vx, right? But what's Vx?
6 volts, yeah.
Right?
6 volt drop.
And let me just, I like using colors. Does that make sense? Now, I'm going to use another probe over here. We're there, right? So if I wanted to calculate what the voltage is right here, right? I'm going to call this, what do you guys want to call it? Let's call it, I don't know, VT for top. Let me just top. Does that make you feel better?
Yeah.
What's V top?
6 because 12 minus 6 is 6.
Does that make sense? Did I lose you?
Yeah.
You did?
What do you say?
Did I lose you?
No, you didn't lose it. No.
So we went upstairs, right? We went up 12 volts, right? We're going down the stairs by Vx, right? And now what is our voltage? We went up to the 12th floor, right? We're going down the stairs to the, what floor are we on?
6th floor?
Yep, 6 volts, right? Because we dropped by 6.
Okay.
We dropped by Vx to the next floor, which is 6. Yeah, it's funny how this is like 12 and 6 and 6, and it's a little difficult, right? To where I'm trying to explain. But does this make sense, how we can find any voltage node just by walking up and down?
Yes.
Is that good? So, now that we have the voltage right here at the top, right? All right, I'm going to trick y'all. What the voltage is over here?
0.
Does that make sense?
Yes.
So let's see, what color do we want? Let's just keep it like this. What do we want to call this? Plus, minus? We'll figure that out. Actually, because I want to solve for this voltage drop. Are you understanding what I'm trying to do?
I mean, if it's 6 to 0, then it's a 6 volt drop, right?
Correct. That's actually the trick question of the day. V top minus 0, right? which is equal to the voltage drop of 10 ohms, right? Which is equal to, right? Which is equal to I, let's call this I don't know, I mid. Pretty mid, right? Yes?
Oh, yeah.
So then R, what's our resistance?
10 ohms.
So what's I mid?
6. Oh.
Right? 0.6 amps. Does that make sense?
Yes.
So we just solved for the current here. We already have the current here. Now we're left with this final part, right? So, who can recall what we talked about the last class? We were talking about dependent sources, right? What are the 4 dependent sources that we have, or 4 sources? We have a voltage-dependent current, a voltage-dependent voltage source, voltage-dependent current source, and then you got your current-dependent voltage and current source. Does that make sense? So, this current right here is for I of this device. What is this? It's a current source, right? It's sourcing water, right? It's sourcing a flow, correct? What's it dependent on? Vx, right? What's Vx? Does that make sense? And then it forced itself to call this one I, so we're going to stick with I. What's the current going through here? I, right? So we have I is already given to us as 0.1 Vx, right? So what's I equal to? 0.6. Does that make sense? So now that you know what the current is, right? Let's see.
Question.
Yes, yes?
So, would we just add that point? You said that's a current source, right?
Yep,
So
sourcing
would we
current.
add that to the existing current flowing through that?
Let me show you what's going on. So this is a source. It's sourcing current. It's just, if you think about it, it's forcing the current. Actually, better yet, that's why I was asking, what's the current going through this resistor? I, right?
Okay.
Are you thinking like, oh, we're adding more water from here, right?
Yeah, I thought it was like another inlet. You know, like more. It's adding to the current.
We'll answer that question in a few seconds.
Okay.
So let's keep that as a thought, and I'm going to show you exactly what's going on. Okay? If we know the current, right? We have the resistor, right? What's the voltage over here?
Yeah.
What's the voltage over here? Vy, right? Which is equal to I times R, right? What's the resistor? 2. What's our current?
6.
What's Vy? Any questions about that? All right, now let's go back to what we were talking about. Like, okay, is it adding more current to what we have? Yes, no, maybe. I'll answer that question for you. Like a little trick. Would it bother you if I do the following? Let's see. Want to see if I can do something funny. Let's call it source. And then let's call this one. All right, I'm gonna start tricking everyone. You guys like tricks? Yes? No? No. Let's call this one, I don't know, I something. I1. Is that good? And then let's just keep this to 1 ohm and 2 ohms. And we're going to make this dependent on I1, right? All right? But now I'm going to do something funny. 0.0 or whatever. Does that make sense? So I have a current I1, right? Let's just make it equal to, I don't know, 10 amps. Right? What's I1? 10 amps, right? And then I just put a gain of like 0, right? What's 10 times 0?
0.
All right? So the current that's going through here, or that it's sourcing, is just 0. Does that make sense? It's just an open.
Wait. Sorry, one more time.
So I have this current dependent current source, right?
Okay.
And it's dependent on this current right here, right? I just called it that. And I just put a gain of 0. So it's off. It's turned off. So technically it's like, think of it like a gate or some type of like current amplifier. And it's just set to 0. It's off. So no matter what my current is, it could just be, I don't know, 100 amps, right? This is just going to source 0. There's not going to be any current. I source, right? What's the current going through here? Right? Does that make sense? So technically, if the current here is 0, right? And if I were to do the following, right? What's the voltage there? Wrote it down, right? What's the voltage over here? Why? Because when there's no current, that means there's no voltage drops. That means it's technically just 0 and 0. That make sense? Did I lose you again? Or no?
Well, I'm wondering, so you're saying the current source is 0, but what if it was like 2?
2?
Yeah. Like 2 amps.
Like you want 2 amps to go through here?
Yeah, or like what if it was I1 times 2? Like that was the
Then let's just change it to I1 times 2. That makes sense?
so is it adding current?
No, we're just multiplying.
Okay.
It's an amplifier dampener.
It's a current source that's dependent on a current.
Okay, I got
Or
it.
better, okay, let's make it even more simpler. Let's do Vx, right, from the problem, right? And I'm just gonna call a random Vx of 10 volts, right? And let's just change this to I source is equal to 2Vx, right? It's a current source, right? That's dependent on Vx, right? If I have a gain of, usually it's written as some kind of gain times whatever your thing is, your voltage. Does that make sense? You have a gain of 2 or 0 or minus 1, right? So if it's 0, or point is, what I'm trying to say is this is forcing a current to go through it. Or are you trying to talk about, are you saying like, okay, I have 100 amps going from here, right? How do I verify that it's not going in there, right? Was that the question you're trying to ask?
I think I was just confused on what that symbol meant, but I understand it now. It's just like an amplifier.
Yeah, it's basically when you see this kind of symbol, it's a dependent source. It's depending on something else. So when you start taking our advanced level classes, like our electronics courses, you're going to realize that there's devices that are dependent on other devices, such as current mirrors, voltage amplifiers. Like, for example, how do I say this? Like, you have your speaker, right? That's a bad speaker. I don't know what a speaker looks like. Let's just say speaker, and our input is some signal Vx, right? And our gain here is, I don't know, 2, right? And then our output is just equal to gain times Vx. Does that make sense?
Yeah.
So what happens if the gain is 0? Output 0. There's no voltage. Does that make sense?
Yes.
Everyone clear about what we're trying to do right here? Voltage dependent current sources, etc. All those 4. Now let's prove this, because I think that's the next question next thing I want to talk about, because I know you guys are starting to do your circuit analysis. let's use a calculator. You guys like calculators, right? LT Spice is, I already talked about this a little bit at the end of the last class, is a calculator. Let's just treat it like that. So this is kind of like a semi-tutorial on how to even use this. So I want to solve for what we have right here. Let's go back. Actually, let me label it so I don't lose this. Let's prove that I actually did, that we all did this right. Is that good? All right, let's go. So we need a voltage source. So you can either press on this little key, it's the component key. You can either press this, or you can just press P for component. Or to get a voltage source, let me just type this. You can type in voltage, right? Or use our hotkey V for voltage. Make sense? Now I need a resistor. And then I need another resistor. And now someone's saying, how do I get a volt or current supply, voltage dependent current source? Let's check that out. Let's see. It's going to be one of these. Voltage dependent current source. Right? That's what the homework problem was asking for, right? Because we want to know Vx. Okay. Then let's do another resistor. R for resistor, by the way. I didn't tell anyone that. Okay. Zoom out. There we go. You can do W for wire or press this button right here. You like the colors?
And this is 4 connectors on the current source.
Right? So let's do the following. How do I want to do this? Let's type in a node, label net. Let's call this one N, right? Then I'm going to call this one V top. Is that good? Let's draw some wires. You like that? And then let's call this one, I typed in N for label, VY. And now someone's shouting, where's Vx? So Vx is going to be this voltage drop. But based on our homework, let's go back to this. Let's see. How do I want to do this? Let's go over another sheet. I don't like this. Draw it super quickly. I'm calling this one Vn right here, right? And then we call this one V top, right? And then we call this Vx, right? Is that clear? In just these two terms, what is Vx equal to? Is that good? So, yeah, not necessarily we're like, oh, there's a label for the actual resistor, but we can also use these as our node voltages. Is that clear? You ready? Let's type that in. So we know that we have this plus potential right here, right? And it's asking for Vn, right? So let's just do that right here. I'm going to draw a little label. I'm going to do Control C for copy. You guys like these shortcuts? And then I'm going to probe this part right there. Control C for V top. Does that make sense? So what are we doing? 12 volts. Where's it 12 volts? And then this right here was 5. This right here was 10. This right here was 2. So let's see. Now we want to type in our gain. All you got to do is just do 0.1 and then times Vx. Actually, no, that's probably it. That's right there. Okay. Let's see if that works. So this is the gain of our current source. And I didn't have to type in Vx or the labels because that's right here for me. That's already done for me. V top and Vn. Does that make sense? So now the next thing I'm going to do is we want to start calculating the circuit, right? So Where is our run? This used to be a running man. Let's run this guy. Let's run it for 1 second. This is a transient sweep or transient time, so we're simulating in time. So we're doing 1 second, and I'm just doing this for fun. What's the voltage going to be here? 12? You like that? What's the voltage over here? 6 volts, like we calculated, right? What's the voltage over here? Actually, better yet, let's look at the current. And I don't like that direction. So let me show you a trick that I show to all my senior level classes. If I click on this resistor, right? Let me double click on it. You see it's a negative number, right? But I'm trying to go the other way. So there's 2 ways you can cheat this. Click on it, and then just force it to go where you want it to. Rerun it. Now it's positive. Does that make sense? Because the direction, technically, it's LT Spice is saying, this is my reference. And it's referencing 1 point, just plus to minus. So this is plus to minus. Does that make sense? What did we say the current was in this resistor? 1.2 amps, right? And now we're going to take this voltage drop. Let me just type this right here. If I double click here and double click or 1 click right there, let me see. How do I add a trace? Let me type this in, but it's not going to make any sense. Vn minus voltage of V top. Does that look like 6 volts to you? Type it in red. Right? Yeah, this is a bad example. I wish I could have showed you how that voltage drop is. But this right here is our voltage drop of that resistor. Does that make sense? What's the current that we expected over here? 0.6 amps? Let's see if it's correct. Oh, no, it's not. Why? Oh, you just got to change the window resolution. Let's see. Does everyone know that 600 milliamps is equal to 0.6 amps? Does that make sense? Is this bringing your confidence back?
Yeah.
So now you can use this as a way to like verify all your homeworks. Actually, every homework from now on till 400, all the circuits courses, you can use LT Spice. It's one of the greatest calculators that I believe so. It's a great simulator. You can verify anything you want. So, and then what's our current here? What did we say? 0.6 amps.
Yeah.
What's the current in here that we just said? So you want to know what's funny? Is that we get 1.2 amps coming through here, right? But we get half of it going here, and we get the other half going here, right? So let's just do something funny. I'm gonna do this 0, and let's tell you where that current's going. If I run it again, 8 milliamps. Well, it changed our thing, that's for sure. But let's see the current here. What's that? Yeah, just 0 nanoamps. But what can we? What's nano? That's 10 to the minus 9, right? Nanotech feels cool, but nano is just so close to 0 that we can just round it down to 0. Does that make sense? So technically, there's no current going through here. Want to see? If I just do this, I zoom this, that looks like 0 amps to me, right? Does that make sense to everybody? Any other questions? What's our next homework problem that we want to do in class? Let's save this as, let's see, look at all these courses I got. 220 discussion, let's call this one EE. 220 lecture, 3.
Discussion for all those classes?
Huh?
Are you leading discussion for all those classes?
Yep. That's what I'm here for. Or actually, let me just change this back to, come on, double click, point, what was the problem, 0.1. There you go, solution to that problem. Does that feel good?
Yeah.
Let's do another way of doing this. So if I were to do this, save as, call this one B, save. Let's run a different type of transient. Instead of a transient, I'm going to run a .op, and that's just an operating point. It just stabilizes our circuits. In future classes, you're going to see like sinusoids and things starting to settle, like, water when you hit it and it starts settling. This is like a stable state. And let's run this. Run. Does it look better? VN, VTop, VY, IR run. Current in R and the voltage drop of R1 is 1.2. And then why is this minus? The current in V1. Because, well, it's going like this. Actually, no, let me see. Well, technically, the current for a voltage source, this is what I was going to tell everyone how to do this. If you guys want to have better homeworks, let me just stretch this out. Oh. Press S to stretch the wires. Move and stretch. That's the command. Oh, that's not a good stretch. There you go. Oh, come on. Now let me show you a trick that I knew. So this is how you measure current in one of these types of circuits. Is you just put one of these dummy voltages, right? And you just set it to 0 volts, okay? And I'm going to call this one my current, let's just call it ammeter. Does anyone know what an ammeter looks like from physics? So this right here is just going to mimic our ammeter. This is just something I'm calling. And now let me just run this. Ammeter, 1.2 amps. Feel confident? All right, what's our next question? Because I want to start answering questions now. Who's our next person to write something on our board, or what's going through the lectures? Because this is something I want to hammer. Because I know there's 2 professors. They're doing 2 things. Hopefully they're the same. Homework problems. This is what the discussion page was for. I want to do homework problems with you guys. Yes, no? What's another problem that we have? Anybody? Take a minute. Let's create another circuit. Actually, do I want to create another circuit? No, let's keep that empty. This is page 3. What other topics have been talked about in the lectures? Did you guys go through mesh analysis? No? What's the latest topic?
We just started diodes.
Diodes.
You went over.
Yeah, he went over
what a
it.
diode is.
Yeah, he went over what it is.
You talked about KCL, KVL.
Is this for Dr. Pushkin or
Yeah.
what's Dr. Zhu doing? KCL, KVL? How do you feel about everyone learning 2 different things? I want the other professor. He's cooler. Man, why can't David just be our professor? He actually makes videos. Anyways, and let's just talk about the diodes, because I don't even know why they're trying to do diodes in the first place.
You said, I remember our professor saying that usually we don't learn about diodes in this course, but the book he chose went over it, so we taught it.
Yeah, this is a diode. Another way to say a diode is like a LED. And all it does is it supplies a constant voltage, or not supply a constant voltage. It requires a way to power it on. And usually it's 0.7 volts. And why is it that? And why is it not like 10 volts or whatever? Well, semiconductor-wise, you'll see in future classes that this voltage is something that's physically attached to all these diodes. Better yet, do you guys know what a diode looks like? Guys want that introduction? Diodes. I don't like those ones. These are my favorite diodes. LEDs. Light emitting diodes. Yes? Say that again? Yes, somewhat. It's more like a, it's like an on voltage of a p-n junction. So when you turn on the voltage, when you apply a voltage potential, there's like a current that runs through your diode. So you'll realize that when you take, I think, 320 next year, when you start learning that, hey, there's a reason what that voltage is, and then it's a property of temperature. There's also voltage itself. You'll learn about that physics next year. So what other questions were there?
What's like if I was making a product, why would I want a diode? Like, what's the application?
A diode. You guys want me to talk more about diodes?
What's new? It's interesting.
What's an interesting thing? Well, one of the first things you can do is just create a circuit like this. Plus, minus. And then you got your current. And all you can do is just turn on a light bulb, right? The other thing you can do is, let's see, because I want to talk about this, but this is way too crazy.
No.
There we go. Triangle. But we're not going to go over this in class. And then this right here is plus, minus. And then this right here is our AC signal. You can build rectifiers with these kind of things. AC to DC rectification. That's why we would use rectifiers for, or diodes for. It's for rectification, or basically if I know this is going to be 0.7 volts, I want V out to be 0.7 volts. That's when you would want it. Does that make sense?
So you use it to change the AC current to DC?
Yeah, this right here is our full bridge rectifier. That's what we would use these diodes for. And then there's other applications such as like inverters and other little things, but that's out of the scope of this class. That's the next year's problem. What other things have we gone in the class?
We also went over like resistivity and conductivity.
Resistivity and conductivity. Has he gone through IV plots with you guys?
He did like a little bit today.
So I'm going to create a plot right here where the x-axis is a term of voltage, right? Right? And then this y-axis is going to be a function of current. Does that make sense? And then one of the things I'll teach everyone about is the resistor. V is equal to IR. Does that make sense? This right here is called your resistivity. Right? But the one thing is these right here are called IV plots. And usually it's the x-axis is our voltage, is our thing that we like to like turn our knobs, make sure we change our voltage, right? And then we usually like to see current coming out. That's usually our output. So this is actually rewritten as this, right? Which is our conductivity. Does that make sense? So let's just put it into simple terms. Let's just say I have an infinite resistor. I'm infinitely resisting, right? So if my resistance is super high, right? Let's just say infinity, right? Really buff resistor, right? What does that mean about our conductivity? It's not conducting. So if we wanted to do this, 1 over infinity, right? It's just, well, 0, right? Okay? Now let's just say I have the best conductor in the world. It's super great. Things go through it. You just throw electrons and it's a freeway, right? What does that mean about our resistance? No resistance, right? So that means if our conductivity, usually some people call this one G, conductivity G, I think that's what it is. Or I think there's another joke that people like. This right here is considered in terms of ohms, right? And then there's another one that people created. This one would be in terms of, I think someone tried this, mho, because it's backwards for ohm. That makes sense. but this is our conductivity. Usually it's in terms of a G, right? So if our conductivity is infinite, let's just say, for example, right, our resistance is going to be 0, right? That's probably what they were talking about in class. Does that make sense? Any other questions? How's the homework going, though? Good? Did they already get your first grades? Yes, no, maybe, plus?
Our first homework's due
Due day? Midnight? Let's do some homework problems. No? Let's write this as 4, 5. Who wants to do mesh analysis? Let's see. Plus, minus. Yes, yes? All right. What do you have?
Voltage across current through a certain device given by VT. Yeah, I'll just go on. Sorry.
We have technology. Let's see.
132.
132. Let me take that picture. Wait, 132? Voltage across. Wait, let me just take that. Let me see if we can do this. 132, the voltage and current divide. Thank you very much. All right, let's save this for later. The voltage across a device.
Oh yeah, B should be on that one.
Which one?
The 132B.
132B.
Or you're not doing 32 or
Wait, 132, right?
Sorry.
It's going to equal 100 volts, 1 minus e to the minus 0.2 t. And then I is going to equal 60 e to the 0.2 t. This is volts. This is milliamps. The instantaneous power, PT, at t is equal to 0 and t is equal to 3. Well, if our power is a function of time, right? What does that mean for our I? It's a function of time, right? It's also a function of time. Does that make sense? And we're talking about instant. We're just talking about one window of time, instant. So t is going to be instant. So we're just talking about t is equal to 0, right? So that means I is equal to 0, or I at time is equal to 0, or equal to 0, right? And also for, I'm just going to write this over here. Does that make sense? Right? So then what does that mean for this right here? So if I were to do 60 e to the 0, right? Is that good? Times 100, 1 minus e to the 0, right? Is anyone clear about what I'm trying to do? What's e to the 0? Just 1, right? Times 100, right? What's e to the 0? That just cancels out right there, right? Turns to 0, right? That means what's our power? Or, yes, 0. Thank you. 0 watts. Is that good? Now, problem B, the cumulative energy delivered to the device from t is equal to 0 to t is equal to infinity. So for that, I think there's an equation over here. Let me remember. This right here is 6. This right here is 7. Because energy is also a thing that we got to also figure that out. So there's going to be an equation. Cumulative energy delivered to the device from t is equal to 0 to t is equal to 100. Let's recall, because eventually what we're going to try and do is it sounds like an integral. That's what I'm thinking it's going to sound like. T is equal to
energy is power times time.
huh?
Is energy power times time?
power times time. Is that what the equation is?
Yeah, I think it's in my book calibrate.
Is that what it is?
Yeah, like the kilowatt hours, like kilowatt times hours.
Kilowatt times time.
They get the measurement of energy would be kilowatt hours.
Because I think one thing I remembered is, let's see. So I'm going to teach some cool little things. If I were to have some type of blip or some pulse of energy, right, that's going to be some value, right? But power, well, that's just a sinusoid. If you think about it, there's an equation for this. Let's see. What did your book say? Calculate power from energy. Let's see. That's it? Is there an integral for this one? I think that's all it is. So I think from what I'm thinking, I'm not so sure, is if I were to draw this as v of t, and this is time, and we are going from 100. Initially, our voltage is going to be that over time. Let's see. That t is equal to 0. That's going to be 0. So if I were to do the following, sounds like a charging equation. I'm just going to assume it's this. No, it goes up quickly to 100 volts. That's probably what I'm thinking the voltage is going to be. Is that good? And if I were to draw current, and then our current goes down from 60. And it's going to do this. Is that good? I think from what I'm thinking, it's going to be a mix of these two because I'm not so sure what's going on.
What I was thinking is like since the bottom graph current actually like as it goes to infinity, it goes to 0.
Yep.
So 0 times anything, no matter what the top graph says, the voltage, anything times 0, these power is voltage times current. Right?
Yes, yes, and it's asking until
So anything times 0 is 0. So I was thinking the power, as time goes on, will eventually go to
cumulative energy. Yeah, because eventually this is something that's already calculated. Actually, I'll give you another hint because I think you hit a good light bulb for me. Because one thing I taught to my signals and systems people is that when you have energy, you don't have power. But when you have power, you don't have energy. That sounds like a double whammy thing because I'll tell you this. And that's why I kind of like panicked for a little bit. P of t, or power. This is a sinusoid. This sinusoid is going to have some kind of power to it because it goes from positive infinity to negative infinity in time, right? But the energy in here is just 0 because it all averages out. I see what you're talking about. But if it's just this blip of energy, it just exists for just 1 second, right? It's not going to have power. I think that's what I think that's what's going on, right?
It says in the book that power is the derivative of energy.
Derivative of energy.
They gave us P equals dW dt.
Is this about part B?
Yeah, this is part B. That's what we're trying to solve.
I thought it was take the integral.
Yeah,
It's a big like
I
integral.
did the integral from 0 to infinity of P, like V
V
times I.
times I.
That's what I was thinking too.
Product more like this.
Because if you just do this V of t and then P of t, that's or I of t. This is what I was trying to do. Is that what was going through everyone's minds? Do an integral?
That's what I.
Yeah.
That's what I'm thinking too. Because you're trying to technically calculate whatever energy just exists there. Is that good? Any other questions?
I got 50.
They're teaching this in this class, right? I'm just trying to teach circuit analysis. That's what I'm being paid for.
Can I see so like what the answer is for B? What you get
For B,
for 32B?
30. 32B.
That's what that is.
Well, let's just solve for it. Yes, yes?
32B, and that's what milliamps amps do we
Convert milliamps to amps?
Yeah, for the 60 mA.
Well, you can, but just keep your m or your 10 to the minus third power somewhere, and then you can bring that back up to your equation. So let's just try this. See if I can remember my calculus. Yeah. Think you guys are going to use calculus every day? Maybe. Let's just call this from 0 to infinity, right?
Yeah.
I mean, if you use a calculator, I wouldn't mind.
So let's just see. We have a 60 milli, then we have 100 volts, right? From 0 to let's just do T for now. What's our equations again? Let me see. 1 minus e to the 0.2 t times e to the minus 0.2 t dt, right? And then if I wanted to combine these two, this is my amp or my amplitude, right? It's just a constant volt number right here, right? So let's just do this. 0 to t of e to the 0.2 t minus, and then this is just going to be equal to, tell me if I'm wrong. No, because you add this, right? Yeah, you do. Is that what everyone got? Did I do my calculus correctly? No, we didn't even do calculus yet. And then all you got to do is just amp of e to the 0.2 t dt minus 0 to t e to the 0.4 t dt. Does that make sense? We're all getting this? Okay, and now let's solve for our grand finale. Trying to figure out what they're trying to show you in this, because this is circuit analysis, not calculus. Well, you do need calculus for something. A is equal to, when you take the integral, you do, let's see, because if you take a derivative, I'm trying to remember this just comes out and you just get the exponential, but it's going to be, tell me if I'm wrong. Is that good? Then minus 0 or 1 over 0.4 e to the minus 0.4 t, right? From 0 to infinity, right? Is that good? So if I were to do the following, let's do infinity here. What happens when this goes to infinity? 0, right? What happens when this goes to infinity? Right? We just did the infinity case, right? Now we got to do this other big case, and I'm just going to do this curly bracket. Minus. What happens when this is 0? So it's going to be 1 over 0.2, right? Minus, double minus gives you a plus, right? Then what happens when this is 0? Yep. And then, does anyone know how to do this one right here? Let's see. See if I remember this. No. And do I want to calculate this one right here? Point.
It's negative 2.5
Negative
in the calculator.
2.5. And then what's our amp, or what do you call it? What's A? 60M times 100, right? And this is going to equal 6,000 M, right? But what's M? 10 to the minus 3.
Yeah.
So that means this is 1,000, right? And this, or it's, let me write this again. 6,000 divided by 1,000. All right? 6. Good? 6 times minus 2.5. right? And what's 2.5 times 6? Well, 12, and then you get a 15, right? That good?
You're supposed to distribute the negative to the negative 2.5, so it's positive.
Oh, thank you. And then those two negatives turn into this. Is that what everyone got?
Yeah. So the cumulative energy being delivered to the device is 15.
Let's just call it joules. That's what I'm thinking it is. The unit of energy is in joules. Is everyone clear about that? Man, they're giving you these really tough problems. I was sweating here too.
That's I think that's tough because it's like one of our first homeworks.
Yeah, because one's going through KVL and KCL, which is our domain, but the other one's doing joules, and nothing wrong with that. But so I think one thing that's going to help me out, and especially is going to help you guys out, is I'm going to do another discussion board, and I want people to start throwing questions. And then better yet, when you type in your questions, type in your professor section or whatever it is, so I can start polling what you guys are doing in class. Does that make sense?
That makes sense.
All right, so I want people to start using the discussions, type in who the professor is, and then I'm going to start doing logistics on what's going on in these classes.
Do they use the same books, the two professors?
Yeah, they're using the same book. Let me see. So yeah, just let me know what you guys are doing. And is there any other questions? Does anyone know what LT Spice is? Yes? What's your question? 3 minutes.
I thought this was at 3:45.
Oh, no, 1 hour.
Question 3. Just calculating current with like switches between two like resistors.
Oh, I like this one. Let me take a picture of that.
Okay.
All right, we have a great question that I really like to see. 6, 7, 8. Did I just say that number out loud? 6, 7? 10. Here's our final question of the day. Let's zoom through this. Get you guys' money's worth. Okay, this problem of the day was $40, $250, $100. It says calculate the current I in the following circuit when the switch is in position 1. So A. What's IA? I'm just calling that. That's what it's asking for. What's IA? So we have a resistor, right? Or let's just type our voltage, right? Or V is equal to, hold up. V is equal to IR, and we have IA, right? We have our resistance, right? What's our voltage? What's the voltage over here? 0, right? And then what's the voltage over here? What's the voltage over here? What's IA? .4 amps. Boom, done. Now it says, find the current when the switch is to position 2. There we go. You like that? Quick math. Right? What's the voltage over here? What's the voltage over here? What's IB? Does that answer your question? Easy? Any other questions? Yes, no? Have a good day, everyone.